Hi, my name is Nurin Batrisha. I will present about the case study 1 is optimizing production in a ceramic studio. Claycraft Studio, a local ceramic business, specialized in handcrafting to popular products, which is bowls and mugs. Each week, the studio operates under tight resource limitation with only 100 hours of labors and 120 pounds of clay available. Each bowl takes 1 hour of labor and consumes 4 pounds of clay, yielding a profit of 40 ringgit. On the other hand, each mug requires 2 hours of labor and 3 pounds of clay, generating a profit of 50 ringgit. With a high demand for both items, the business must decide the best combination of bowl and mugs to produce in order to maximize its weekly profit without exceeding the available labor and clay. So for the objective, determine the number of bowls and mug Claycraft Studio should produce each week to maximize profit under the given resource constraint. So for the step 1, problem formulations. So for the decision variable, we are analyzing a Claycraft Studio that produces 2 products, which is bowls and mugs. So we define X is the number of bowls produced, Y is the number of mugs produced. These are the value we want to determine. So next, let's look at the constraint. The production process is limited by 2 resources, which is labor and clay. For each bowl takes 1 hour of labor and 4 pounds of clay. Each mug takes 2 hours of labor and 3 pounds of clay. The total available labor is 40 hours and the total available clay is 120 pounds. So we write the constraint as X plus 2Y less than or equal to 40. This represents the labor constraint, and 4x plus 3y equal or less than 120. This represents the clay constraint. We also include non-negativity constraint, which is x greater than or equal to 0 and y greater than or equal to 0, because we cannot produce a negative number of items. And the last one is objective function. Now the goal of this problem is to maximize the profit. So each bowl generates a profit of 40 ringgit and each mug generates a profit of 50 ringgit. So the objective function is maximize Z equal to 40x plus 50y. Let's move to the next step, which is step 2 of our linear programming solutions. Now that we have formulated our constraint and objective functions, it's time to visualize the problem by sketching the visible region on a graph. Plotting the constraint lines. How to do this? The first one, we need to convert the inequalities into equation to plot the boundary lines. From the step 1, we had 2 main constraints, x plus 2y equal to 40 and 4x plus 3y equal to 120. So this is the final. We already convert the inequalities into the equations.
Assalamualaikum warahmatullahi wabarakatuh. My name is Putri Nurul Farhanu binti Roslan. I will continue the last presenter explanations, which is step 3, plot the graph. Alright. For the step 3, after we get the constraint, which is labor constraint and the clay constraint, we have to plot the graph, which is for the labor constraint is 20 40, which is in the graph 20 on alright. Next is clay constraint area, which is we have to plot the 30 on axis x and 40 in axis y for clay constraint area. Next, after we have already plot the constraint, clay constraint and the labor constraint area, we could see that there is a feasible solution area, which is R as the place where clay constraint and the labor constraint across. Next, after we have already plot the constraint, clay constraint and the labor constraint area, we could see that there is a feasible solution area, which is R as the place where clay constraint and the labor constraint across. Next, After we get the feasible region area, we move to the optimal solution coordinate, which is we get a 3-point in graph, which is A, B, and C. For A, we get the axis X 0 and 20 for axis Y. For B, we get a 24 in axis X and 8 for axis Y. And for C, we get the 30 in axis X and 0 for axis Y. Next, I will explain how to get a point B. We use a simultaneous equation, which is 1x plus 2y equal to 40 for equation 1 and 4x plus 3y equal to 120 for equation 2. And how do we get for the equation 3? We multiply 4 in equation 1, then we get 4x plus 8y in equal to 160. And how do we get a axis y for point B? We minus the equation 3 with equation 2. Then we get a 0 plus 5y equal to 40. Y equal to 40 divided by 5, and we get a y equal to 8. And how do we get the axis x for point B? We substitute y in equal to 8 in equation 1. 1x plus 2 multiplied with 8 equal to 40. 1x plus 60 equal to 40. 1x equal to 40 minus with 60. Then we get x equal to 24. Then we get the point B, which is 24 in axis x and 8 in axis. Lastly, I will explain for the last step 4, which is a corner point. And since the maximum z, we get the 4 corner point, which is the first one is 0, 0, which 0 in axis x and 0 in axis y. Z equal to 40 multiplied with 0 plus 50 multiplied with 0, we get RM 0 ringgit. Then the next corner point, we get 0, 20, which is 0 is axis x and 20 in axis y. Z equal to 40 multiplied with 0 plus 50 multiplied with 20, then we get RM 1000. For the third corner point, we get 30, 0, which is 30 in axis x and 0 in axis y. Z equal to 40 multiplied with 30 plus 50 multiplied with 0, then we get RM 1200. And the last corner point, we get 28, which is 20 in axis x and 8 in axis y. Z equal to 40 multiplied with 24 plus 50 multiplied with 8, then we get RM 1360. Since the maximum Z equal to RM 1360, therefore maximum profit at point B, which is 24.8. For extreme corner point solution, we get for point A is RM 1000. For point B, we get RM 1360. And for point B, we get RM 1200.
Hi guys, my name is Vinraj. So today I will be presenting regarding the second case study, which is we choose about minimizing the production cost for packaging materials. Okay, now we'll be looking into the scenario. EcoPack, it's an industry that produces two types of recycled packaging. Recycled packaging materials. Which is the first one is box type X and also box type Y. Each type of boxes uses different amount of cardboard and plastic liners. They use cardboard and also plastic liners. The company wants to minimize the total production cost while meeting certain material usage requirement and resources limits. the material that will be used in EcoBag is cardboard and also plastic liners. Okay, for the cardboard units, it requires 2 box X and also 3 box Y. Okay, and the limit will be combining both will be required 50 units of cardboard. Okay, that will be produced. And then the second one for the plastic liners requires 4 box X and also 1 box Y. And the limit will be 20 units minimum. Okay, the cost for box X will be $4 and also for box Y it costs $5. Okay, here's step 1. First, we have to formulate the NP problem. Okay, NP problem. The objective, the minimum objective that we can get is CC is cost. Okay, cost equal to $4 X plus $5 Y. Okay, the subject constraints is 2x plus 3y less than or equal to 50 cardboard usage, and the second subject constraint is 4x plus y more than or equal to 20 plastic liner usage. The third one, x and y is more than or equal to 0. Okay, for the second step, we need to construct a graph. Okay, we need to construct the graph and also plot the constraints line. But before constructing the graph, we need to know the x value and also the y value for both equations, for both constraints. So let's find the first equations, x and y value. Okay, for constraint 1, cardboard usage. The equation is 2x plus 3y equal to 50 units. Okay, in order to find the x is that we need to set the y to 0. Okay, first equation 2x plus 3, the y value is 0 and equal to 50. So 2x will be 50, therefore 1x will be 25. So now we can get the x value. Okay, x value is 25 and y will be 0. So so in order to find the y-intercept, we need to set the x to 0. Okay, 2x will be 0 plus 3y equal to 50. So if 3y equal to 50, then we need to divide over 3. So to get the 1y value, which is 16.67. So now we can get the y value. Okay, x is 0, y is 16.67. So for the constraint 2, second constraint, plastic usage, 4x plus 1y equal to 20 units. We need to do the same steps. Okay, to get the x-intercept, we need to set y to 0. Okay, 4x plus 0 equal to 20. So to get the 1x, we need to divide it by 4. So 1x will be 5. So now we can get the x value, x 5, y 0. So the next one is to find the y-intercept. We need to set x to 0. For y value is 0 plus 1y. For the x value is 0 plus 1y equal to 20. So we can get the y value directly upon y value, which is 20. So x will be 0, y value is 20. So now we can.
Assalamualaikum and good day to all. My name is Ikram Afiq bin Faizal. In this video, I'll be explaining step 3 in solving a linear programming problem, which is sketching the feasible region. Once we translated the problem into mathematical inequalities, usually involving decision variable like x and y, we move to this important step, which is step 3, involves sketching the feasible region. This is the area on a graph that shows all the possible solutions that satisfy all the constraints. Here's how we do it. First, convert each inequality into an equation by replacing the inequality sign with an equal sign. Then, plot the line of the equation This is called the boundary line. Decide which side of the line to shade based on the original inequality sign. For example, if the constraint is x plus y less than or equals to 10, we draw the line x plus y equals to 10 and shade the area below the line since we're dealing with less than or equal to. Do this for all constraints including non-negativity constraint like x more or equals to 0 and y more or equals to 0, which ensure the solution stays in the first quadrant. The feasible region is the overlapping shaded area that satisfy all constraints. This is the region where we will look for our optimal solution. Make sure to clearly mark the corner points of this region because those are where the optimal solution usually lies. That's it for step 3, sketching the feasible region. It is a visual but very powerful step in linear programming as it helps us understand to set off possible solution. Thanks for watching. The next step will be explained by my team member. Thank you.
Okay, my name is Muhammad Isan, so I will continue for the next step. Step 4, find the corner extreme point. Okay, for this step, in linear programming, the best solution whether you want to maximize or minimize, which is always lies on the corner points of the feasible region. Now, we look at the graph, which is there are shaded gray area in our feasible region where all the constraints are satisfied. Then the blue line show the constraint 2x plus 3y equal 50, which is represent the cardboard limitation, and the green line 4x plus y equal 20, which is represent the plastic limitation. Then to find the intersection point of the two lines, we solve the equation step by step. First, we multiply the second equation by 3, which is 4xy equal 20 becomes 12x plus 3y equals 60. Then we subtract the first equation from the new one, in bracket 12x plus 3y minus in bracket 2x plus 3y equals to 60 minus 50, which is this simplified to the 10x equal 10, so x will be 1, x equal to 1. And then now we substitute x equal 1 back into the second equation. 4 to 4 in bracket 1 plus y equal 20, so y equal 16. Okay, and then this gives us the intersection point in bracket 116, which is it marked in the red on the graph. On the graph, we also identified two more corner points in bracket 50, where the green line intersects the x-axis, and another one is in bracket 25, where the blue line intersects the x-axis. So the corner points, there are three corner points, which is 116, 50, and 25. Okay, so for the next step is step 5, evaluate the objective function, which is we see from this result, we see that the minimum value of C is RM20, which is occur at the point of 50, which is the optimal solution for our minimization problem. Then, so to minimize the cost, the company should produce 5 unit of product A and 0 unit for product B. So the conclusion is minimize C equals to 20 RM20, which is uh, the corner points is 50. That's it. Thank you.